Hey guys, your boy Chill here. Welcome back to another devlog from Project Chill. It's been a hot minute. I haven't had a lot of time to work on this stuff, to be honest, but I did get a little bit of time and I did make a little progress, and I want to just kind of keep you guys up into the loop. Again, these devlogs aren't going to be part of the main series for the Chill framework. I just want to kind of keep this stuff separate. I want that series to be very focused and not have a bunch of videos that are just dead ends, but I also want to keep you guys, appraised of what's going on as I'm trying to figure out how we want to architect all this stuff. So, what have I wrought? Well, first, let's just check to see where we are at here. What do we have? What are we working with? So we got this application here. It is drawing a buttload of animated sprites, about 250,000, not about, exactly 250,000 on, I think, like 32 sprite sheet variations. So it's the same sprite, but I basically cycled the colors. So from the point of view of the program, it's rendering 32 separate sprite sheets and 250,000 instances. And so I've written some basic benchmarking code that is timing on the CPU side, how long it takes to update all the sprites and then how long it takes to draw it, basically to spit all their data out over to the GPU. That does not count how long it takes the GPU to actually render them. We'll get into that a little later. And the other thing that I've been using as a kind of benchmarking helper tool is a program called PresentMon, which tracks presents, frames that have been presented to the screen, and we can see ours window app here. We're getting about 80 frames per second here. Now these values are not the same as I get. They're not even close to what I get when I turn OBS off. When I'm recording, it's a lot slower. So I'm going to be showing you guys from my results. I'm going to be showing you the values that I get measuring when I'm not also recording screen capture. So this is the final commit I covered in my previous devlog video. Here I split files basically into .h and .cpp files. I split a bunch of things out. Nothing that interesting there. Another thing I did is I created these backend agnostic interfaces for a bunch of the different things that you deal with in the graphics layer. So texture, sprite codec, sprite batcher, resource loader. Now they all have an interface that is not tied to any specific implementation like, Direct 3D 12. Another thing I did here, a bunch of cleanup, is I had the active window class in main, and I just pulled that out to its own header source pair. I also pulled the globals out into their own header here, all those inline const exprs. Just some general cleanup stuff. Now, the first real significant change here, and this is only a change in how we are instrumenting, how we are measuring performance, is I created benching stats. So I made a class bench data, and you throw your data points in here, my time measurements basically, and it allows me to get a percentile, like the worst 1% of all the values. So if you look at the output from my CPU measurements now, you see I have the average, but then I also have the 99 percentile and the 90 percentile. So the 99 percentile is basically saying what is the worst 1% of measurements that I've gotten. Those outliers are pretty important because they impact the feel of the game. Even if your average is very fast, if every 1 in 100 frames is much slower, that's gonna cause like a jitter in your game. It's gonna cause a little jump, and it doesn't look good. It doesn't feel good. It impacts the game feel. So it's good to look at these percentiles and not just the average. The other thing that this class does, which is kind of useful, is I can ditch the first n% of samples. That's not the worst 10% or whatever. That's just in terms of the time history, ditch like the first 1 second of data, because at the very beginning when the program is running, things are warming up, cache is warming up, and so those measurements aren't indicative of your steady state performance. And so you can see here, after the game loop exits, I'm going to ditch the first 10% of samples in my update and draw measurements, and then I'm just outputting, the average, the 99 percentile, and the 90 percentile. So that stuff out of the way, what's the actual graphics stuff that I experimented with in this pass? Well, let's take a look at what we are doing with our sprites. We transfer the sprite data from the CPU to the GPU every frame for every sprite. And so for every sprite instance that we have, it's a quad. It's got 4 vertices. And in that vertex data, we give the position, texture coordinate of that vertex on the sprite sheet, and then the parameters that we use to create the transformation matrix, which is the translation, the scale, and the rotation, and the index into the array of textures where the sprite sheet actually is. And we duplicate this data for all 4 vertices, although they'll have different position and different texture coordinates. Translation, scale, and rotation and atlas index should be the same for all of these. So position is, R, G, we have X, Y, Z basically, although the Z isn't really being used, so let's not count it. So if I do the math, there's 9.5 floats, because this is R16, times 4. So 38 bytes for 4 vertices is 152 bytes being transferred per instance. And this is contributing. This is, I believe, what's mostly contributing to the sprite draw time, being much larger than the update time. The bottleneck is transferring the data across PCIe bus using, the uncacheable, right, combining memory. And we've done what we can to improve that, but now it's not. Like, I can throw more threads at this problem. It doesn't really take any less time because the bottleneck is, I believe, the bandwidth there. And so the question is, can we do anything about that? And right away, like I've already mentioned, we notice that there's information being duplicated for all these vertices. It's the same. The translation is the same for all the vertices, scale, the rotation, the atlas index. So if we could find a way to just reference that once, that would save us a lot of time. And I found a very nice approach to this problem that has yielded some pretty big gains. So we're going to use what is, I believe, called instanced rendering, where you actually have multiple vertex buffers that you bind, and some of those vertex buffers are consumed per vertex, and some of them are only consumed once per instance, and then copied to all the vertices in that instance. So, for our data, for our per vertex, I managed to basically squeeze it down into only one 2-dimensional position per vertex. And all the rest of the data goes into the per instance, which is only done once per sprite. And if we do the math, it turns out that this structure in here, it's only 42 bytes. And so we are actually getting 3.6 times the bandwidth efficiency by using this instance drawing approach. Now you might be saying, well, Chili, you didn't add the bytes that are per vertex. Like, this should be an additional 8 bytes that are per instance. But no, this is free. This is free. It does not happen per instance, because what I actually have here is I have a tiny static vertex index buffer. It only has 4 vertices in the vertex buffer, and they are locked to, this was a mistake, this is not -1, 1, it's actually -5 and then 1 and then it's -5, 5, and then it's 5, 0.5, 0.5, -0.5, -0.5, and 0.5, -0.5. So what it is it's a box where the width and the height are 1. It's a unit box centered at the origin. And that's all I need for my vertex data. And that one box goes for every sprite, no matter what its dimensions are, no matter where it is on the texture map. It serves them all, because this information is used to transform these vertices to what they actually should be. So basically, these numbers are only needed to map this information into what it should be. If that makes any sense. Probably doesn't make any sense, but maybe I'll be able to explain it a little more. But the upshot is we got 3.6 times our efficiency. We're not like plus 20% or plus 50%. We're plus 360% efficiency. That's pretty good. That's pretty good. So let's take a look at what changes are necessary. It's pretty minimal. You'll need to change these 3 files. So the vertex shader is where the majority of the work is being done. If we look at the input, before we had these inputs. per vertex. Now they're coming in through two streams, one per vertex and one per instance. And it's just the stuff that I've shown you in the picture. What you see, the generating of the matrix is exactly the same. Nothing there has to change, but we do have to now recover our actual position and our actual texture coordinates based on, again, our unit position values and this per instance data. So if you look here, we're taking in destination dimensions, and that is basically the dimensions of this sprite, how it should look on the screen in pixels. So how big is it, in pixels when, the scaling is at 1. So it's very easy to recover your vertex position for any given vertex based on this, because we have a unit square. So if we multiply that unit square by the dimensions, we get the actual position for any given vertex. Now the other thing here is recovering the texture coordinates. That's a little more tricky. I break it down. So what I'm looking at is, okay, I got to recover what is the texture coordinate for this specific vertex that I'm working with. What do I have? Well, I have the rectangle of textures, the texture rectangle, meaning I have the left, top, right, bottom values in a float 4. And I need to recover a specific pair of x, y from these 4 values. How do I do that, given that I have this, unit position, which is one of these boys, except it's 0.5 and not 1. First, I figure out what's the top left of my texture. It's obviously going to be textrex.xy. So that's my top left point. So if I was working with this vertex, that would just be this value is what would be my texture coordinate. But I don't know which vertex I'm working with. I only have the value. So how do I derive it? Well, I derive my dimensions of my texture rectangle, which is again just the width and the height by subtracting the left and the right, top and the bottom. Then I generate the axes, which is a little more interesting, but basically our static input positions go from negative 0.5 to positive 0.5. But for texture coordinates, the top, they start at 0 at the top left, and then they go positive to 1 on this side, and they go positive down to 1 on the bottom. So we got to remap that. So this is mapping from negative 0.5 to positive 0.5, maps that to 0 to 1, we're adding 0.5. And this one is going to map y from 0 to 1, but it's also going to reverse the direction. So it's not pointing up, it's pointing down now. And so once we have these 3, we can then calculate our UV for this specific one by taking the top left texture position and multiplying the texture dimensions times the axes. So if it's 0, we mapped from negative 0.5 to 0. If it's 0, we multiply by 0, it stays here. But if it's 1, it's going to go here. Or it's going to go boom, boom if they're both 1. Or if only y is 1, then it's going to go down here. And so this is how we generate the texture coordinate that corresponds to the vertex we're working with. So now we have the shader working like that. How does the CPU side code change to match it? And before we had a structure to represent the vertex data that we were transferring. Now we have 2 structures. The per vertex data, which is going to be very simple, just a 2-dimensional position, and then the per instance data, which has all the stuff matching up with our shader signature. Now our vertex buffer and our index buffer become static, and the only thing that's dynamic is our instance buffer, the per instance data. So that's what's switching over here. So now instead of having max indices and max vertices, these two kind of codependent things that we're tracking, we just track max instances, which is much nicer. It's just the number of sprites that you can draw at any given time. Now this is actually an interesting thing that we have to look at, just part of the Direct3D API. Now that we're working with instanced rendering, the layout is going to change. We're going to use things that I've actually never used before in videos. So it looks very similar here, but before these were all just per vertex data. Now I've separated, I put a little new line in here to separate the per vertex data versus the per instance data. They both go in the same layout, but you specify them. So here I'm saying this is per vertex data, but these ones are all per instance data. All right, so this value here, these ones, that's the input slot. So we're binding 2 different buffers, the static vertex buffer that is used for all instances, and then the buffer of instance data, where there's one entry per instance. So that's our slot 0 and slot 1. Now where's the other? The instance step rate. So you can copy one element of our array of per instance data. You could copy it for multiple instances, but we're just, every element in that array is the data for one instance, not for multiple instances. So the step rate should be 1, and it is 1. It's right here. There you go. All right, so that's that explained. And that's one of the biggest changes you need to make on the CPU side. Now, the other changes is obviously now we're creating our vertex buffer up front. So here I create the vertex buffer resource and the view of it, create that up front in the constructor. Starting batch, we are going to map into instance buffer. We're not mapping into the vertex buffer. It has become a tiny static buffer. Down here when we are drawing, so here's where, you know, all the magic happens. You see now, because we're not writing per vertex, it actually becomes a lot simpler. We just write the data for the instance, and all the figuring out of the individual texture coordinates is happening in the vertex shader now. So this becomes a lot simpler, which is nice. It's always nice for your code to get smaller. For the static index data, instead of, you know, repeating the same pattern for every single instance in a big index buffer, the index buffer now becomes 6 values, 0, 1, 2, 1, 3, 2. That's it. And that is used for every single instance that we draw. And for the vertex buffer, like I said before, it goes between -0.5 and +0.5. And this is just written, copied over, and Bob's your uncle. I'm not going to bother, you know, running it and showing you again because it looks exactly the same. The only thing that changed is the performance, which changed quite a bit. So if we look at this was measurements done in the previous system, all per vertex data without ditching, you know, the first 10% of samples. Here's when you ditch the first 10%. Numbers look better because, you know, you're removing some garbage values from the measurements. Here's what it looks like with all the data being instanced. So if we look here, some of the measurements look like, for example, the sprite update is actually a little bit slower, although this might be variance. But the draw is like almost twice as fast. Same number of threads. So that's huge, right? Again, this is on the CPU side. This doesn't necessarily correlate into twice as much FPS because the GPU is doing its work on a different timeline. But it does actually give me more FPS. Like before, I was running, you know, maybe around 120 FPS. But when I made this change, it's probably not like 144. It's probably more like 100 and maybe, I don't know, like 32 or something like that. Because it depends on how many sprites are actually on screen, because some of them are running off and on screen. But in any case, it was noticeably faster, like at least 10% faster going from here to here, which is great. But doubling the speed at which we can do this on the CPU side is very nice. And before, like this was basically limited. I could double the number of threads, but I would barely get an improvement on this speed. But I can actually increase the number of threads here and the number goes down even more. So very nice improvement there. That is definitely staying. We are going to be using instanced rendering for our sprites in the final product. It's just a much better way of doing things. All right, now there's one more kind of, you know, graphic side thing that I explored, you know, direct 3D technique. So we'll cover that in this video, but before I did that, I did a couple of, you know, smaller changes. Here, my interfaces, I changed it. Let me see if I can find some of them. Like you can see a lot of these things working with XM float values and stuff like that. But these things, as much as possible, I like to just use the agnostic ones. Although this is in the D12 namespace, so it's not terrible to implement them with XM float. But as much as possible, I just decided to move things over to my own, you know, math type implementations here because it's more convenient to work with them. If I need like some kind of operation, I can add it to, you know, as a member function. It's a lot cleaner to work with. Now here's a feature that is added that I think is pretty important for a sprite. And that is the pivot point. So you can specify per sprite, what is its pivot point? So say I got like a sprite here and I place it at, 0, 0. Where do you think it was? Like if I'm saying I want him to stand at 0, 0. If I just put this sprite at 0, 0, it's probably going to go like right here, like at the center point of the sprite. But what you usually want is if he's standing at 0, 0, if I set him at 0, 0, his feet should be here. And that means he is at 0, 0. And that's what the pivot point is. And also like rotating the sprite. Like what point do I want it to rotate about? Like, do I want it to rotate about this point? Or do I want it to rotate about like the center of his body? Or do I want it to rotate around, where his feet are? And that's what giving you a pivot point allows you to do, is to set that and set it per frame. Because some frames are wider than others. Like look at this frame. This is really wide because he's slashing a sword if it's part of his sprite. But normally if he's just standing, the sprite would be a lot narrower. So the pivot point, the point that is his origin, would be different. Wouldn't be at the very center of the sprite, because that would be here. That doesn't make any sense. For this sprite, it makes sense for it to be here, for this frame. For a different frame, it might make more sense to be, in the middle of the frame. So adding a pivot point, it ripples to a bunch of different things. The vertex shader has to take it in. That is going to be incorporated into the transform matrix. It only really affects the translation of the sprite, but it is influenced by scaling and rotation. Put that in the per instance data here, and it comes into the sprite batcher draw, and then it's forwarded to that draw call from, sprite frame. And I did a little test here just to make sure that it was doing what I expected it to do. So let me just build that and show you. So you can see a single frame of that sprite. I scaled it up real big, but I set its pivot point to be at the base of the feet. So now when it rotates, it's rotating around his foot here. It's being placed at 0, 0 and rotating. So that is working, and it's nice to have in there. All right, now let me cover the last thing I wanted to talk about here, which is my experiments with further trying to reduce the amount of data being transferred to the GPU. So what you notice with this, we've reduced a lot of redundancy here, put it all in this per instance data. But a lot of this instance data, like the rectangle for the textures and the dimensions that the sprite should have on the screen in pixels, and the index of the atlas, these all don't change. Also the pivot point, they don't change from instance to instance. It's the same. It's a property of that specific frame of that sprite. So this is all static, really. And we're just transferring it over every time. But we don't need to. We could extract all this out into one of two things, either a constant buffer or a structured buffer. And then per instance, all we would give here is a single index. Basically, replace the atlas index, and it would say, what is the frame index? And you would use that to look up into your constant buffer or your structure buffer to get this frame data, the texture rectangle and its dimensions in pixels. And then you would reduce redundancy even more. So I'm going to, give you some spoilers. I did that. It didn't really improve on these numbers here that much. There was a measurable improvement, but it wasn't very big. Now it might improve, it might enable me to throw more threads at the drawing and to have a higher ceiling, basically, before I bottleneck on the bandwidth. But the other more important thing that I've been kind of ignoring here is, okay, I've been measuring these CPU side things, and that's interesting. It's very interesting because the original reason why I instrumented this stuff was to check to see if I virtualize the sprite interface, how would that affect the overhead? And it does affect the overhead, but it's not a big deal. At an enormous amount of sprites, orders of magnitude more than you would normally see in an average game, it's still very fast. And I am limited on my GPU side, which I'll get to in a second. So I'm GPU limited here. And I thought, well, if I do the structure buffer stuff and it improves my CPU speed even better, that's not bad. Maybe we could do it. But it's not even that big of an improvement. So I've decided not to do this. not to use structured buffer or constant buffer for that data, and just to put it all in the per instance dynamic upload. But that being said, let's just do a quick review of what it took to actually do that experiment. So I now need to upload, more data. And at this point I figured I should make like a class to just encapsulate the process of, creating a static buffer, creating an upload buffer, and copying from the CPU to the upload buffer, and then issuing a GPU command to copy from the upload to the static buffer. So I create static buffer class here. That works for, there's a base one. This is meant to work. Put the common logic for all buffers: vertex buffer, index buffer, constant buffer, and then inherit from that to create, static CPU buffer, which is what I call, something that can be either a vertex buffer or an index buffer. So it's just templated on the view type, and it works like that. It's just all the stuff that I've already shown about, you got to write commands to copy, and then you got to collect the garbage. And this makes the sprite batcher cleaner. They look at all the code that's now been removed from here. A little bit has been added, much has been removed, because it's all factored out into its own class that handles, the concern of how do I get this data into a static buffer. So separation of concerns, yay. So I did that, and that was a prelude to me putting frame data into a constant buffer. So here's some cleanup. And so here is me putting the frame data into the constant buffer, which, as you can see, is a complicated change by the number of files that had to change, although many of them are just a small amount of changes. So I deleted sprite frame and I moved it into sprite codecs for this reason, because now it's kind of intertwined with the codecs, because every frame is referencing something that's like the codecs is what is going to manage all of the frame data in the constant buffer now, and it will bind that together when it binds the array of textures. So that means that the sprite frame is kind of entangled in here, which I don't know, it's not, in many ways it's not great, but that's the way it's done. So now the sprite codecs itself maintains an array of the sprite frames, and it uses that array to generate the constant buffer. So you add frames to this codecs, and when you're done, you finalize it, and that will generate the constant buffer, and then that constant buffer will automatically get bound when you bind, the array of textures here, the sprite atlases. And if you look at the batcher, you see the root is going to change because now it's got this constant buffer in here. And the procedure for like when you are finishing a frame changes because you need to bind some stuff. Sprite codecs needs finalization. The binding doesn't change at all because it's encapsulated in the codecs. So it's just, the get table handle still works the same as it was working before. But if we look at the vertex shader, we now have a struct frame and then a struct frame array, which is just 2048. If you're using constant buffers to do this, you have to specify a bounded size. And then I do a constant buffer frame array, and I use that to load the frame data, and then that frame data is just being used as it was being used before, except instead of coming in this per instance data, now it is stored in this FD structure that I reference here. I mean, that's it. It looks exactly the same, and it performs pretty much exactly the same. It's more complicated is basically the end result. And so I figured, okay, let me try structured buffer. The difference between a constant buffer and a structured buffer, because they kind of work the same. Like if you look at my vertex shader here, so I replaced this, the frame structure definition stays the same, but now I don't have a definition of a structure that's just an array of frames. I just have a structure buffer frame, and I don't have to give it a specific, maximum size. It's unbounded. Whatever size I bound, that's okay, as long as I don't index past what I've actually bound in there. But the rest of the code is basically the same. So it's like, well, what's the difference between a structured buffer and a constant buffer? And the difference is how it is actually implemented in the hardware. Constant buffers are loaded into registers for the shaders, which have a fixed size. And it doesn't do well if it's divergent across, your warps of your execution. Structured buffer it works a lot more like a texture that you sample in. So it does not load it into registers. It's not pre-jacked. It's doing lookups, and it doesn't have any hard requirements on size. If your constant buffer is way too big, it doesn't fit in the registers, that means it has to execute the shader more times or something. It's not great. So there's trade-offs, there's differences between the both, and generally the best advice is just try both and see which is faster. So that's what I did. I tried both, and they're both kind of similar, to be honest. And they're not, either one did not really address, it didn't give me any more FPS. There's really no difference between these, and there's very little difference between doing this and just using instance rendering, putting all the data in the instance buffer. So that's what I'm going to do. I'm putting all the data in the instance buffer. But in case you're interested, let's look at how a structured buffer is different than doing it with a constant buffer. So I added another static buffer type thing, another class called a structured buffer. So in addition to static constant buffer, we now have structured buffer. And it has its own, write copy commands and whatever, all that good stuff. Like a static constant buffer, it needs a constant buffer view, but structured buffer needs a shader resource view, which is the exact same type of a view that a texture requires. Because like I said, it's very similar to a texture and how it's actually implemented. So sprite codex now is not going to have a static constant buffer, it's going to have a structured buffer. And a lot of the stuff is just the same. It's like instead of making a static constant, I make a structured buffer. Because all the differences are encapsulated in the class of structured buffer that I created, which is the way you want to do it. So this code doesn't really change, except just the names change. And here in my descriptor range, instead of being range type CBV, it's now SRV, because it's a shader resource view. One interesting thing, though, that can maybe trip you up is because it's a shader resource view, it is going to be bound to the same, like register here, the same series of registers. So you got to make sure that they don't overlap. And so I decided T0 is going to be for my structured buffer, and then T1 is going to be for my textures. But there are many different ways. You can use different register spaces, or you can control the visibility between the vertex shader and the pixel shader so that they don't see them, and then they don't get the conflict. But I just decided to give them their own number and just call it a day. Okay, so earlier I said that this was the last thing that I did. That was a lie. There was one more little experiment that I made. So basically, after doing this work, I realized something that is, pretty obvious, but I got a little lost in the sauce, because originally all this measurements that I was doing was to measure the impact of virtualization, and I'm now way past that. I'm into like optimizing the rendering pipeline. But optimizing the rendering pipeline doesn't have anything to do with these numbers that I'm measuring here. This is all on the CPU side. Well, I don't know why that's like that, but anyways. So what I should really be measuring is, well, how long is the GPU taking to get its work done? Because it's clearly, at least in my mind, that looks like it's the bottleneck. I mean, if you look at my numbers here, like it's making maybe in total, maybe 2 milliseconds if you add in extra work for other things that have not been measured here. 2 milliseconds. So that should mean that I should be running at 500 frames per second, but I'm not. I'm clearly not. I mean, again, this is limited by my refresh rate, but if I pump up the numbers here, these numbers go up, but it doesn't add up, is basically. The CPU is not the limiting factor. So how do I verify that? And a very good way of doing that is to use a program called GPU View. So here's a capture I took in May 28th. It is running Chill Engine 350,000 sprites. So it's not limited by your refresh rate at all. And let's just zoom in here, because this is too dense to see anything really. So we'll zoom in on a likely candidate area here. It's not the most user-friendly tool, but it is what the pros use. Okay, so here we see window app. Here is its device context. Here's where it is in queuing work. And we can see here, it never is starved for work. The queues are always maxed up. You got double frames, which is what you would expect. And here, the hardware queue that is doing the work, there's no like gaps in here. We can zoom in even further. And if you do something, you can increase, it filters out the threads, basically only showing you the ones that are doing the most work. But you can add more threads. So show more threads. Now we see these 4 threads here. And this is very interesting because we have 4 threads. And also when I run this, I'm running with 4 worker threads who are doing the drawing or the updating and then the drawing. And that's what you see here. You see an update. Then you see it waiting basically on a fence value, waiting for resources to become available. And it is going to draw the 4 frames that were previously, the 4 batches of draw command lists that were previously executed. And once it's done that work and it can present that, then resources will become available and it will unblock, and then it will start to do the drawing step for the next frame. So we see here, like, look at all this blank space on the CPU. This, we are not limited on the CPU, we are GPU limited. This is all blocked up. It's all constipated up here. And here it is flowing free. It's just twiddling, the CPU is just sitting around twiddling its thumbs. So, I mean, obviously, we see right here, okay, I'm wasting my time trying to optimize CPU time, and there is no good reason for me to try to do this structured buffer or constant buffer stuff for the frame data. Just upload it all. It's fine. It doesn't even give that big of a benefit to begin with, and the thing it's benefiting is not the bottleneck at all. So the next step is, okay, well, what the heck is the bottleneck then? And I mean, we can make some guesses, but they're just guesses. So if we want to get some actual data here, I'm running right now on an RTX 3080 Ti. So probably the best tool to check that stuff out is Nsight, because it's going to access all the internal counters, the performance counters that they got there. Let me see if I have my... okay, good. I can still get my old trace that I have here. So here's a trace I made. And you can see here all the sea of sprites being drawn here. And you can see the work being done. And if we like just mouse over here, we can see that the thing that is the biggest, like 92%, is prop throughput. Now, it is very hard to find information on this. They do not have documentation or anything. But ROP stands for raster operation. And that makes sense because we're pushing a lot of pixels. And so we would expect the pixel part of things, and the pixel shader itself is very small. It's what happens after the pixel shader. It's actually moving those pixels and, you know, resolving the transparency stuff. That is what is apparently our bottleneck here. And I don't know exactly what, you know, prop is as opposed to, you know, like ZROP is Z buffer stuff, apparently. And then raster is rasterization, which is, you know, like scan converting the triangles, which you would expect to be in there. And obviously, you know, your memory, your L2, your L1 texturing, you would expect that because you're looking up these sprites to copy the pixels from the texture to the render target. But I'm not exactly sure what prop is. It stands for pre-raster op. And the one small little blurb I could read about it was like, it was saying something like it connects the ZROP to, I don't know, like some other units, to like the pixel shader unit and whatever. So I don't know. I don't know what it is, but it is the bottleneck. And there might be something we could do to like improve the efficiency of the operation of this unit. Or it might be that we're just like approaching the theoretical, you know, limit of how many pixels you can push, because we are, I mean, this test is, you know, like 1/3 of a million sprites, so that's plenty of sprites, right? But I mean, obviously the one thing that you can do if you're limited by your fill rate is Z buffering and leveraging early Z so that you can discard pixels early if they fail the depth test, right? And so that is the last thing that I tried here. And the first thing I did was I had to make sure that depth was working, because what I realized was I wasn't, like, I was only using, they all had this, I just hard coded Z to be 0. So they were all at the exact same depth. That's not really good. So I put that into the per instance data. And in the pipeline state stream, I put in depth stencil state. And I thought it might be enabled by default, but I wasn't sure. So I just put it in here and I made sure that it's enabled. Masks all are what you would expect. I gave all the sprites, a random depth between, 0 and 1. And what I found is that you can achieve a huge improvement. Well, let me step you through it, because it was an interesting process for me. So the first thing I tried after doing all this was, okay, so first I disabled this alpha test. Now what that's going to do is that's going to mess up your scene composition. But this was just testing my theory. It wasn't like I'm actually going to use this. I was just trying to see if early Z would make this a lot faster. So let me see if I can just run it. So here's what it looks like. And obviously you can see that disabling the depth discard is not great. But early Z doesn't work if you put that in your pixel shader, because it can no longer trust the Z value, because you're screwing with it, right? You're screwing around with the Z value, and so you lose all those optimizations. So just to test my theory, I disable that, and this is what you get. But what I got when I did this is like, okay, so in order for this to work, you really have to sort your sprites so that you draw the in-front sprites first. That way you get maximal discarding. So I did that. I sorted my sprites in my batch so that the front sprites come first. And when I did this, the program ran slower. I got less FPS. And I was like, wait a minute, that doesn't make any damn sense. Because, I mean, like, if early Z isn't working, I should just expect the same FPS. Why? How does changing the order in which I draw the sprites make it slower? And when I dig down into it, what I realized, there's two things really. So one thing was that for what I was doing during that testing, if you look at global, I had set the number of batches from 4 to 1. I was testing another theory, which proved to be true. And the theory was that if I am GPU limited, there's no real sense in increasing the number of batches. And indeed, making more command lists just adds a little extra overhead for the GPU. So it's actually a little slower. And that's true. It is slightly slower on the GPU if you split it up into 4 command lists, but obviously a hell of a lot faster on the CPU. So that was one of my tests. So I had it set at only one batch, was not running multi-thread on the CPU side. And that was fine because I was GPU limited. Now, when I sorted my sprites, I changed the order of traversal in memory. They were generated in one order and they exist in the heap in one order. So if I don't sort them, if I don't rearrange the sprite pointers in my container, then I will be iterating through the heap memory mostly just in order. But if I sort them, I'm now jumping around in the heap memory, and that is messing up my lookup, my latency. And because I only have one thread going, that now suddenly the CPU became my bottleneck and I was losing a little bit of frames per second. If I turn it back to 4 batches, then I was golden. And if I turn it to 4 batches with this off, with depth enabled, and sort it, it's actually much faster. It's way faster. But obviously, like that's not doable. That's not doable because it looks like trash, right? But maybe in certain situations with certain kinds of sprites, it might be possible. I won't go into any details right now, but in some situations, it could be an optimization that you could finagle. But in general, you can't have this. You can't have nice things, and you'll just have to settle yourself with maybe like 500,000 sprites maximum if you want to run 60 FPS on an RTX 3080 Ti. So maybe not 500,000 sprites if you want to run 60 FPS on a different card. But considering that most games are like maybe a few thousand sprites at most, that's not too bad. That's not too bad. The end result of this is, obviously, one of the things you have to always be cognizant of here is the real cost of virtualization here isn't just the virtual call. That's actually the small part of it. The real cost is that if you allocate things on the heap, then you're not guaranteed to traverse them in order. Even if you sort your container of things, your pointers, the objects in the heap don't change. They don't change their address, which is very good for many things. Changing addresses causes a lot of headaches, but it's not good for traversal. And in our current situation here, even with that, it's not a big deal. If I have 4 threads, it runs perfectly fine with an insane amount of sprites that you would normally never have. But in some situations, in some games where you, for whatever reasons, you are running an insane number of sprites, maybe then you don't want to allocate them on the heap, and that's fine. The chill engine will be perfectly amenable to you rolling your own implementation that doesn't have any of the virtualization in it. So that'll be fine. You can use the lower levels of like the sprite batcher and the render pipeline, but have your own implementation of the actual sprites themselves. So yeah, just lots of interesting learnings there and fun little gotchas. Long story short, we will be rolling with instanced rendering, and we will put all the sprite frame data in the instance data, even if it is a little redundant, because it's easier that way. It's more flexible from a programming standpoint, and the benefits of putting it in a constant buffer, a structured buffer, are just, they're not there. The juice is not worth the squeeze. But yeah, going forward, future work, the first thing I'm going to do, this is something I was hurting for while doing all this testing, is I'm going to get in here a command line parsing utility that'll enable us to define command line switches and parameters and use them, consume them very easily and very conveniently from our code. Very good for the developer experience, because it's so annoying having to like change like one value in globals and then recompile the program to do a different test. I want to be able to just change the command line parameter and do that. So I'm going to add that in the infrastructure. I'm actually going to put it down here before I started all this experimenting, and then rebase this stuff on top of it is like what I'm thinking I'm going to do, because I want that, and I want it now. But after that, I think the next step is to create the simple sprite layer that is basically mimicking the programmer experience, the developer experience that you get with like SFML. Where you can just create a sprite object and off you're running. You don't have to create like a sprite batcher and a codex and all this other stuff and then bind it and the frame. So I want to start work on the simple layer, because that is going to help inform future work on the implementation layers. After I get that done, I want to start work on stuff that is optimized for tile maps. So there will likely be a different thing that is similar to sprite batcher, but that is much more optimized for what you would typically see in rendering tile maps. And I want to look at how to let advanced users basically implement their own effects for sprites and tile maps. So they can use the stuff that's in the framework, but inject their own shaders and have their own specific layout of per instance data that they can forward to their shaders. That's what we're looking at going forward. The next video is definitely going to be on developing the command line interface utility that will be a permanent fixture of the chill framework. And until then, thanks for watching. Hope you enjoyed the video. If you did, click that like button. It helps a lot. And I will see you again with some more chill framework.